Hi calculus students, welcome to your first set of video notes. Yay! Calculus is so much fun. So these notes are going to be on finding limits graphically. And first of all, I'm going to give you an informal definition of what is a limit. So we're going to say a limit is the intended height of a function. And I just want to be clear that when we're saying height, what I mean by height is if you think about the x and the y axis, the height is always going to be a y value. And now I'm going to introduce to you guys the limit notation. So we would write the limit LIM of some function f of x. And underneath you put this little x goes to, or x arrow, and then some number I'm going to call c is equal to L. So that might look very unfamiliar to you now, but I'm going to break it down and we're going to try to understand what each part of that means. So first of all, the way we would read this is we would say the limit as x goes to, or you could also say approaches, c of f of x is L. Okay, so the idea here is, let me kind of break things down for you. So remember that the limit is always a y value or a height. So this L, the thing on the other side of the equal sign, this L is always going to be a y value. And then it says the limit as x goes to, or x approaches c. That's this notation down here telling you what is x going to and then what is the intended height. So c will always be an x value. Okay, so this might all seem kind of abstract because we're using C and L instead of actual numbers. So we're going to look at some examples which will hopefully make this more clear. And for each of these examples, right now you only see an equation, but we're going to sketch a graph for each. And then we're really thinking about this graphically, visually, as we think about what is the intended height of a function. Okay. So the first one is h of x is equal to x plus 1. So I'm going to sketch a quick graph, and you guys should do the same. The idea would be, I'm just going to try to get a quick idea of what this looks like. X plus 1, so that means I have a y-intercept at 1. I'm just going to kind of do a couple tick marks on my x-axis and my y-axis. So I'm going to put a y-intercept at 1, and then it's 1x plus 1, so a slope of 1, so I'm going to go up 1 over 1 and just get a couple points on here. So now we have our graph of h of x. So suppose I asked for the limit as x goes to 1 of h of x. So notice that now I'm replacing that c with an x value, a number. And I'm wondering what is the intended height of the function, or as x goes to 1. So I can kind of trace along my x-axis and say, well, here's where 1 is on the x-axis. What's the intended height of the function? Well, it looks like that the height of the actual function is 2. So that's also going to be our limit. So for this example, the limit is the same thing as the function value, because at like h of 1, when x is 1, the function is also 2. So sometimes your limit is the exact same thing as your function value, and this is kind of like the obvious situation, okay? Kind of point that out. They're the same. Okay, now our next example, I'm going to kind of draw a little divider, is a little bit more complex to think about. So we have f of x is equal to x squared minus 1 over x minus 1. Now we're really thinking about this graphically, so I'm just going to talk us through how we can graph this function. You could always put this into your graphing calculator and see what it looks like if that helps you. But I'm just going to quickly show you that we know x squared minus 1 on top can be factored into x plus 1, x minus 1. And then we see we have this factor of x minus 1 on top and bottom. So that means that those can kind of cancel out. And if you recall from previous years in math that when you have the same factor top and bottom, that's a hole in your graph. So really this is going to look like the graph of x plus 1, because these will cancel. But at x equals 1, this function doesn't exist, because when x is 1, we have 0 in our denominator. So my graph here is going to look really similar to my graph in example 1, except I'm going to have a hole at the point where x is 1. So when x is 1, y is not 2. So we get this hole. Okay, so notice, pretty much the same graph except for the hole. And just to kind of jog your memory about domain and range, or at least domain, our domain here would be from negative infinity to 1, but not including 1, united with from 1 to infinity. And so basically it's all real numbers except for 1. Okay? And I'm just going to annotate some of what I was saying. So we have f is undefined at x equals 1 because there's a hole. So now we're going to think about the same limit as x goes to 1, but now of f of x. So as x goes to 1, what is the intended height of the function? So this one is a little more conceptual, but the idea is if you kind of run your pen along the graph, as your x values are getting closer and closer to 1, your y values are getting closer and closer to that hole. And that hole happens when y is 2. So even though my y value never gets to 2, the limit is still 2, because that is, like, the key word in our informal definition is intended. It looks like it's going toward, it's intending to be at 2, even though it's not 2. The function value is undefined there. Okay, so we have one more example. So we have like our function, I'm just going to write what I just said. So we have our function, our limit is equal to 2, and I'm just going to say even though f of 1 is undefined. Okay, so our last example is a piecewise function. Now notice the first piece of this piecewise function is the exact same equation from example 2, and the second piece is just the value of 1. Oh, I realized that I forgot to write something in here, so really what we want to say is when, I forgot to say like the domain restriction, so we want to say when x does not equal 1 for the first chunk, and then we want to say when x equals 1. Okay, so now what does this graph look like? Well, the first chunk looks exactly like example 2. So I'm going to redraw that. And then when x is 1, we have the value of 1. So I just should have a dot at the point 1, 1. Okay, so now we're once again going to think about what is the limit as x goes to 1 of g of x. Okay, so now I'm sliding, I'm kind of like going along the graph. What value is my function approaching as my x values are getting closer and closer to 1? Well, as x gets closer and closer to 1, y is still getting closer and closer to 2, even though my function value is this little point down here at 1. So my limit is 2, even though g of 1 is 1. Okay, So we kind of see three different types of situations here. One where the limit and the function value match. One where the function is undefined, but there still is a limit. And then one where the function is defined, but the function value is not equal to the limit value. Okay, so moving on to the next part of the notes. I'm going to kind of introduce you a little bit more to the notation, this idea of left and right-sided limits. Okay, so the idea is that we see in this notation there's either a little minus sign next to the C or a little plus sign next to the C. And those mean something very specific. So the minus sign means the limit as x approaches C from the left. And if you think about it on a number line, so left, that's like negative, right? That's the negative side of the number line. So that's kind of like the negative sign here is kind of cluing you into the fact that you're coming from the negative side of the number line, which is the left side. And then the plus sign means, I'm just going to kind of put these little quotation marks to mean that I'm like bringing down each word from the line above. So we're all the same language. The limit as x approaches C, but now instead of from the left, it's from the right side. And that's the positive side. Okay, so we're going to kind of see that sometimes the left and the right limits match, and sometimes they don't. Sometimes they match the function value, sometimes they don't. Okay, so we're going to run through some examples. This would also be an opportunity for you. You could pause the video, try out some of the examples, and then press play on the video to see if you worked out the same solutions as I did. That just gives you another way of checking that you're understanding or what you're understanding. So I'm going to run through these a little bit quicker than I was doing before. So the first one says the limit as x approaches 1 from the positive side. That plus sign means from the positive side or from the right of f of x. So I'm going to start on the right side of my graph. So like here's 1. I want to start to the right of 1 and start going toward the x value of 1. What is my y value approaching? It's approaching 1. What if I come, now the second one, b, from the left side? The negative sign is there. That means coming from the left. So I start over here on the left and I'm tracing along my graph. What is the intended height of my function here? Still 1. So now what is the intended, now part, it should say C, but it says D. My numbering is off, or my lettering is off. But the limit as x approaches 1, well, from the right side it was 1, from the left side it was 1, so what's the overall limit? Still 1. What's my function value? Well, I have a hole there, so I'm going to say undefined. Okay, so I'm going to flip to the back, and we're going to keep on cruising through. On the second one, again, you could pause and see, can you answer all of these little mini problems, and then press play, and you can see if you get the same answers as me. So on this one, the limit as x approaches 1 from the left-hand side, or sorry, from the right-hand side, that's the positive side. As I come up, I am approaching it a value of 1. From the left-hand side, as I come up, I'm approaching 1. That means what's my intended height from both sides? 1. And then what's my function value? My function value is this point down here. So my function value is -2. Okay. On the next one, the limit as x approaches 1 from the positive side. So I'm going to start on the right and start sliding towards x equal to 1. And my y value is approaching 2. For b, now I'm starting on the left-hand side because that negative side, and as I approach, I see my y value is approaching 1. Now, this is where we get into this kind of not sure what to do with part C. What is the limit as x goes to 1 if my left and my right-hand limits aren't the same number? From the left, I'm approaching 1. From the right, I'm approaching 2. So what's the intended height? I don't really have an answer because I could say one or the other. So instead, we're going to say that the limit does not exist. If you've seen Mean Girls, That's a famous line from Mean Girls, that the limit does not exist. Okay. And then what's the function value of f of 1? Well, I want to see where the closed circle is. So I don't want the value with the open circle. I want the closed circle, so it would be 2. Okay, one more last example. The limit as x approaches 1 from the positive side here. So I'm starting on the right, cruising on over towards 1. I get 1. Starting on the left, I get -1. Since those two values are not matched, that means that the limit does not exist. And lastly, what is the function value? Well, it's neither 1 nor -1. The function value is actually 0. I don't know if you could see that last part. Okay. So we're going to be wrapping up our notes by just quickly drawing some conclusions. The first conclusion and you could also pause here and see, could you figure out what needs to go in these blank spots before I tell you what needs to go in those blank spots. But the first one, it says, if the limit as x approaches c from the right-hand side of f of x does not equal the limit as x approaches c from the left-hand side of f of x, then we would conclude that the limit as x goes to c of f of x does not exist. Okay, and then the second one is it says the limit as x approaches c of f of x equals L. So L is some y value, some number. If and only if the limit as x approaches c from the left of f of x equals L, and the limit as x approaches c from the right of f of x equals L. So basically, these two statements are pretty related, but we're only going to get a value for the limit, and it's going to be exactly what the two left and right-handed limits are if those two match up, right? If these two are not the same value, we have this situation where the limit doesn't exist. So what I'd like you guys to do now is run through all of these examples, and based off of this graph, can you answer all of these? And we will be going over those in class next time I see you. Have a great weekend.